All right, so we are now ready to go ahead and compute the value for dr, okay, based on first order circuits. So to do that, let's go ahead and figure out what the equivalent circuit that will allow me to compute the rise time for the node at B. So what's the equivalent circuit? So the equivalent circuit has to do with this piece here. Okay. So when A turns off, what happens? When A is going to turn off, then let us say my output begins at 0. Okay, and let's assume that. Let's assume that the output starts off at 0 volts. Okay, it may not start at 0 volts, but let's assume that in the absolute worst case scenario, the output starts at 0 volts. Okay, and in that case, I need to find out how long it takes for it to get from 0 volts to VOH. And so the circuit there is the following. When A goes from 5 volts to 0 volts, the inverter X, the MOSFET for the inverter X turns off, and so the capacitor at node B starts to charge up from Vs. Okay, so the equivalent circuit will look like this. So I have a Vs here, okay, and in terms of my MOSFET circuit, this is really my input voltage that is going to be charging up the MOSFET. And then if this resistor is RL, then I have a resistor RL. Notice that this is my Vs node here, and the Vs is going to charge the capacitor through a resistance RL. So that's my resistance RL. And then I have the capacitor CGS. That's my capacitor CGS, and that connects to ground. And Vs in turn also connects to ground. Okay, so this connects to ground, this connects to ground, and so I can connect them up and stick a little ground node here. Okay, so I hope that is clear, that the equivalent circuit that reflects the charging up of the capacitor is my supply voltage Vs, which works as my input voltage, charging up the capacitor through the resistor RL, and so this is the equivalent circuit shown on the left hand side. So the capacitor voltage, this node has voltage VB, that's the voltage across the capacitor. Okay, so this voltage here is VB. And I'm given a few more things. I'm given that VI is Vs. I'm told that. I've also told you that assume that the output starts off at 0 volts. It may not be true, but let's assume that to solve this problem here. So I'm given that VB of 0 is equal to 0 volts. Okay, and I'm trying to solve for t greater than or equal to 0. Okay, let's figure out what the output looks like. Okay. So that is the setup here. What do we see? So we see that the capacitor CGS, capacitance of value CGS, has 0 volts across it to begin with. Okay, so it has 0 volts across it to begin with, and notice that Vs is a larger value. So it's going to start. The volt is going to start by charging up the capacitor. So the capacitor voltage is going to start to increase, and so therefore the model that I need to keep in mind is the model where the capacitance voltage increases like so. Okay, it starts off at 0 volts and it's going to charge up and eventually get to 5 volts. In this case, it's really yes. Okay, so based on the intuitive method that I showed you earlier, I can write down VB directly by inspection. Okay, first of all, I know that this form of the capacitive voltage is given by 1 minus e to the minus t over RC. Okay, but RC is my time constant. It's actually RL CGS. Okay, time constant RC, but really R is RL and C is CGS, so it's RL CGS. So it's of this form. Okay, I know that intuitively. And I also know that, recall what I need to stick here and here. Here I need to stick the initial value, okay, where I start out from, which I know to be 0, so there's nothing there. And the value I stick here is the difference between the initial and final value, and that is simply Vs. That's it. Okay, so intuitively I can very quickly write down VB is Vs times 1 minus e raised to minus t divided by RL CGS. Let's just confirm this. At time t equals 0, this side goes to 0, and so my this side goes to 0, so VB is 0. Okay, so VB of 0 is 0. That makes sense. When t goes to infinity, then the exponent part goes to 0, and so I'm left with Vs. Okay, so after a long time, output goes to Vs, which makes sense because the capacitor is going to look like a long-term open circuit, and as it completely charges up to Vs, the input supply will equal Vs, and so no current will flow, and so that makes sense. Okay, so Vb is given by this expression, and I hammered it out completely intuitively. Okay, so as a final thing, I need to find out the following. I need to find out, okay, so what you need to figure out is what is the time, okay, what is the time t that it takes the capacitor to rise from 0 volts to VOH. Okay, so in other words, the time from the capacitor to go from 0 volts to VOH. Okay, so for VB to go from 0 volts to VOH, and that is my rising delay.